These are typical mains cable ratings. 1mm squared is the smaller lighting size of cable, and that can typically pass 15 amps. These figures can vary depending on whether the cable is enclosed in a metal conduit, underground, standing on the surface in free air. It's all to do with the heat dissipation, because a cable has resistance. The smaller the diameter, the more resistance it will have, and the more it will heat up when a high current goes through it. A 1.5mm cable can pass 20 amps safely, and a 2.5, which is typical for power cabling out to your items, this type of thing, is you can pass up to 28 amps. Well, you think back to those electrode sizes, and that's what you were welding with, those diameters. So it doesn't take a lot of current passing through these size conductors to be able to do a lot of damage, i.e. melt metal. Here, if we take a supply voltage typically of 220 volts, most of Europe, the UK, using Ohm's law, you divide the voltage by the current to give you the load resistance. Another way around of saying that is, if you have, let's say 22 ohms of a load, and you apply 220 volts to it, it will pass 10 amps of current. 10 amps is quite a lot. Obviously 13 amps is a UK standard, but 16 is quite significant. And the load that would draw 16 amps from the 220 volt supply is only 14 ohms. That is not a lot. Let's just continue with this, it will all be explained. So divide the voltage by resistance to get current, or divide the voltage by the current to get the load resistance. For the power, if you multiply the current, which is this here, 6 amp, 10 amp, 13 amp, 16 amp are the typical supplies, multiply that by the supply voltage, 220 volts, will give you the rating, the power rating that each of those cables are able to handle safely without melting. Make that a bit more formal. This is Ohm's law. So the voltage divided by the current gives you the resistance, which we've just done, and vice versa. Voltage divided by the resistance gives you the current. This can be restated, given two of those variables, to get the third in any way. Right, this is where it gets a little bit, it's important, it's something that you need to know. If we take that as being a mains supply to something or other, AC mains, there's your earth. One of these is live and one is neutral. If everything is okay, then what goes down one wire also goes back the other. They're equal. That is how an earth leakage trip works. It looks for an imbalance between the live and neutral current, and if it sees it and it's more than 30 milliamps is a typical setting, it'll trip out to save your life. So let's put that on there. Imagine you have a resistance now between one of those supply lines. It doesn't matter whether it's live or neutral, but let's say this is the live side. And let's say it's rained. So metalwork's got wet, dripped inside, and you've now got a bit of a sizzling going on between the live and the earth. There's a current flow. It might not be much, but there is a current flow. So therefore, this line, the live, is going to be passing not just the load current, it's also going to be passing this leakage current. And if that leakage current is more than 30 milliamps, an earth leakage trip will trip out to save your life. That is because a heart will stop beating at 35 milliamps. A 30 milliamp trip will cut the power before a heart stops beating, so you survive even though you get a shock. Using that Ohm's law that we were just looking at, 30 milliamps from 220 volts is only 7.3k. You only need 7.3k of resistance from there to there to trip a 30 milliamp thing. Now, a little bit more, 6.3k, is lethal. And that's not a lot of resistance. You can squirt water into something, a washing machine can break down and start dripping into the motor, into the coils, the windings, and you can get this sort of a leakage. And if that shorts the live to the metalwork, and it has a less resistance than this, that can kill. So it's very important that you have an earth. If you don't have an earth, the earth leakage trip cannot protect you. It cannot sense if there is a shortage from one line through to the earth. If you have an item which isn't earthed and which gets wet or whatever. So remembering the potential to save your life from an earth leakage circuit breaker tripping if the leakage current is sensed at more than 30 milliamps. This doesn't do you a lot of good. So it's very important that you pass through your own earth between input and output connector, which you can see hopefully in there with the green and yellow cable. It doesn't go anywhere near the controller because the controller, the Chinese controller, does not even have an earth connection on it. There's nowhere to earth. That's no excuse for not passing through an earth from your input cable to your output cable. It's straightforward enough to do. You just get a bit of wire and join it, and then whatever equipment you plug into there will be earthed and you will be safe. The formula for power is similar to Ohm's law, that you have a triangle, one item above the other two, and if you've got two of the variables you can find the third. So the wattage equals the voltage times the current. The voltage equals the wattage divided by the current, or the current equals the wattage divided by the voltage. So 220 volts times 10 amp equals 2200 watts. Which brings us to the current ratings again, and these are the cross-sectional area of the conductors showing how much current they can safely pass without overheating. They will get warm because if you push a current through a resistance, it will create heat. You can't prevent that. All you can do is cool it sufficiently to stop the heat keeping on climbing and melting it. Incidentally, if you have a long extension cable, don't keep it coiled up like the ones that roll up. Don't keep them rolled up because they act as a transformer, an inductor, and that impedes the flow of current. So that itself will cause heat. If you have a long cable, stretch it out in a line, it will run cool. If you keep it coiled up tight, it can run hot, it can melt. You might get shorted turns even. Just to finish off, if we look at these current ratings and their load resistances, so if you're drawing 16 amp from a 220 volt supply, it means your load is only 14 ohms. Now, if you think of what 14 ohms is, it's not far short of a short circuit. It obviously isn't a short circuit, but anything less than 14 ohms is going to draw more than 16 amps. And the conductors are only rated for certain amounts of current. So don't be tempted to plug several high wattage items into one 16 amp supply, because if you don't have adequate trips, circuit breakers, etc., you will overload the cable and you'll basically turn your cables into arc welding rods. I mean, as we saw earlier, you can weld with 40 amps. You don't want to be doing that with your mains wiring. Final thing before I throw the paper away, I mentioned the zero crossing point earlier. If this is the AC mains, then there's a positive half cycle, a negative half cycle. Effectively the power, the RMS power, because it's not a straight line, it's a curve, so it's only maximum voltage, peak voltage at the top of the waveform. Down here there's next to nothing. So if you average that out, you get an RMS value of your AC power. The way a mains controller works, it's got a thyristor or a triac, and it's a silicon switch, which, if this is your 0 point, here's your positive peak and your negative peak voltage, so 230 volts, something like that. The mains controller delays as the half cycle goes up through the 0 crossing point each time. Instead of the silicon device conducting immediately, there's a delay. So it won't switch on and start conducting until, in this case, the waveform starts falling. So it'll conduct only for that small part of the half cycle, not the full amount. And then as it drops below the 0 crossing point, the same thing will happen. There'll be a delay before it then starts conducting. So you only get power for that small little part, then it'll rise above the 0 crossing point, and the same again. So if you sum up these little lumps of power, it's all you have, then your average is very much reduced to what the full average is. Right, so that's us finished with the paperwork.